So I will repeat the first few sentences. I'm sorry about that. This is a tutorial to go from activity maps to layer profiles. I acknowledge those people, and this is a very personal approach on how to get towards layer profiles. There are more streamlined approaches using CBS tools or FreeSurfer, which I never really got to work for my data with a satisfactory quality level. And especially considering the fact that I have partial volume, or like only part of this brain coverage, not entire brains. I want to also show you how simple it is to do layer fMRI. Especially yesterday, Jonathan had this point saying that laminar analysis are too easy. Everybody can do it, right? You don't even need to have high resolution. Just analyze your data across depth. It's that simple. The bigger problem is then how to interpret it later. So to show you how really simple it is, I want to do this a little exercise here. We can do this two ways. We can either do this on the server together, or if you have the right requirements set up on your local machines, you can also follow me locally. The requirements, the things that I need for this session are some C++ compiler. So on Mac, you would need to have Xcode or something similar. On Unix, it's natively included. We need to draw borders later, so any kind of nifty viewer would be helpful. This can be AFNI, FSL View, FSLIs, or ITK Snap. Also for extracting the signals later, I use AFNI. And we need any data, and we can use the data that I prepared already. For example, here are two data sets, layer-dependent high-resolution V1 dataset and M1 motor cortex dataset. On the server, they are at this link. On OpenNeuro, you can also download it here in case you want to do it later at home too. This section of the Google Docs is just like a memory dump of all kind of environment like setups that we might need later. So if you want to do this on your local machine, you need to install LAYNII. And maybe I can show you how to do that real quick. It's as simple as it gets. So for example, right now I'm in my home directory, so I will quickly make a new directory where I dump it and install it. How do I call it? Delete me later. And then we go there. So now we have this empty folder, and we can clone the source code from LAYNII by typing in this command. You can copy paste it from the Google Docs in here. And it complains. Already exists. I was in the wrong folder. I tested this morning on a delete me folder, and now I have a delete me later folder. So in any folder you are, you copy paste the git command to install LAYNII. If you're on the server, you don't need to do that. Just if you are like if you want to do it on your local machine. I will not go through the other requirements later, like how to install AFNI and how to install FSL. If you don't have that already installed, just do everything with me on the server. Okay, this is downloaded now. So we will have a subfolder in there that's called LAYNII, and we can go in there with cd LAYNII. Now we are in the folder with all the source code, and you can compile it with make all. And this basically compiles the C++ code to binaries. There's one important note that in some of the LAYNII programs I use the GNU Scientific Library. If you don't have that on Mac, you can install this with brew install GSL. On Unix machines, you can do sudo apt-get install lib gsl 10-def. If neither of those work for you, you can always just compile the programs that we are using today, which do not have GNU Scientific Library dependencies. So you could just type in make ln grow layers, which will be the program that we use the most. And then you compile just that one alone, and you don't need the GSL stuff. Okay, so there are people in the room who want to do it on the server with me, right? Okay, then I will switch to the server, where you don't need to install LAYNII because it's already pre-installed. And I will quickly log in too. Okay, can everybody log into the server? Show me your hands. Who is on the server? Isn't, yeah. Who is not? Not. Do you need help? No. Okay. Sean, if you want, you can sit here. You don't see the screen. There.
Oh. No. Okay.
I don't think this chair has been playing on.
Yeah, no, my eyesight's not good enough to be able to.
Okay, sure.
Okay, so now I assume everybody's on the server. So the next thing that we want to do is copy some example data. I would like to start with some V1 data because they are already at high resolution and are kind of easy educational example. You can copy them from this path from the Google Docs. Sean, you missed that. The Google Docs is on https layerfmri.page.link.
Is that a layerification?
Layerification,
Okay,
yeah. I'm not sure if it's on the handout.
No, it can tap at my colleague here. Very confused.
You're on there?
Just assume no countdown.
It's also there. I'll send you the WhatsApp link if you want.
Thanks.
If it works. Sorry? Yes, on the server, and we will copy to your home directory in a second. Okay, where are you? There, click on this one. Okay, so on the server, the data are already in the RAID 4 share hands-on _ Renzo. So if you copy this line, the CP -R, and just type it in, CP. Then you should have something that's called v1 _ layering example. So let's go in there with cd v1 _, and in there we have 3 nifty files, a script, and a subfolder for later. Does everybody have the data in there? I'll give you a second. Okay, who does not have the data in your respective? Okay, do you need help? No. Okay. Do you need help? Okay, so now we are in the folder of v1 underscore layering example, and we have these three nifty files. So just to know what we are dealing with, let's look at it. I would prefer to look at it with FSL view. To make FSL view working we need to set all these paths. And then we can start FSL view to open up all these different images with the FSL view command mean underscore vaso. This is an old version, so this is not FSLize. I'm not sure why they installed FSL view instead, but it's good enough for our purposes. So you see it's a slab dataset. If we click on the info here, you see the resolution is in the range of 0.5, almost isotropic. The matrix size is rather huge. We have 26 slices, and we have three different data sets. There is a VASO dataset, which is an activation map, a bold dataset, also an activation map, and the mean VASO. The mean VASO is basically just the mean of the time series, independent if it's activation or rest. This is rather small, so you can always make it a single slice view by using the Control-1 keyboard. But maybe you can also do it here. Single view. If you go to Window and Single View, you can see like only one axis clearer. So I'll close the left window and make it very big, like that one.
I try to use FSL view, saying I cannot connect the apps.
Okay, this. How did you log into
did
your?
you just SSH or did you?
SSH.
You need to have a VNC.
Oh, so I have to work on.
I think if you SSH minus XY,
Yeah.
then the X forward, the X11 forwardings should work.
Okay, but okay. Cool.
So in the meantime, I set this up maybe with more reasonable thresholds from 2 to 8 maybe. I make this not grayscale but yellow. Then the next one, the bold, maybe the threshold is like 4 to 10 or something. I also make this yellow. And in the background, we have the mean EPI, and because it's VASO, it has some inherent like T1 weighting, so it gives us some anatomical contrast. The functional data itself gives us some anatomical contrast. You can like scroll through the different slices here. This is a data set that was acquired with the great help from Sean Merritt at Terra in Bethesda. And the sequence that this was, or the readout that this was acquired with, is from the Bonn group, specifically Rüdiger Stirnberg. So it's a segmented 3D EPI. That's why you can go to these very high matrix sizes without a lot of blurring in the phase encoding direction. So I would like to focus on the visual part down there. So I zoom in. You can zoom in either with the left mouse by just drag and dropping a certain area, or you use the magnification glass up there. So here this looks to me something like the calculus sulcus. If you want to see it, you might see that there's something like a indication of stria genari, like we have brighter voxels. Like this is obviously CSF, the black stuff. Then we have brighter voxels, which would be layer 2, 3. Maybe a line of darker voxels, which might be the stria of genari, and then the brighter one, which would be white matter. We can zoom a bit through it, so we are not perfectly perpendicular. We don't need to be, because it's almost isotropic voxel sizes. In fact, I believe the slice thickness was even smaller than the in-plane resolution, as you can see. Okay, maybe let's look at the quality of the functional data. So this is average of 4 runs, 14 minutes each. For bold, in the thresholds between 4 and 10, you can see these are beta maps, I believe. You can see how it looks. It kind of follows the cortical ribbon. Maybe sometime, like here, you might have a big vein. So it's not perfectly following the cortical ribbon. In vaso, usually it's noisier. You have less significant voxels. However, those voxels that you have are kind of the ones you want. You have a reduced rate of false positives, I would say.
What's the task here?
It's just a flickering checkerboard full field, or full field like as big as the screen was. Yeah. 30 seconds on, 30 seconds off. Yeah. Yes. You mean the Google Docs? You cannot access it? Okay. You can always download it as Word or anything by going to File, down.
Through the VNC.
Explicit
And copy
copy.
paste.
There's an explicit edit paste command in the terminal bar. In the window bar.
Right. You want me to copy this one somewhere on the server?
Yeah.
Okay, let's do that. These are all the commands. How do I do that?
Maybe just create a cat into a text file.
Right. So where do you want it? In the Renzo. Okay. Where do I? In the same folder where we had the data, for example. The data are there. And now we copy paste .txt. Get it. This one. And now we want to copy this one. Hopefully that works. Save. So now you should have a text file where all this is in. It looks not nicely formatted though. Okay. Okay, do you have any questions about the dataset? If not, then I would continue with the first steps that we would need to do to get towards the layering. Okay, so for layers or for cortical depth dependent calculations, we usually need to know where gray matter starts and ends. And this can be obtained from multiple different ways. And Alessio yesterday showed us very good ways on how to do this semi-automatically or fully automatically. FreeSurfer can get you that there, or also the CBS tools. Here, for the sake of being fast, we can also do it manually. In fact, very often I prefer to do it manually because then I have a good feel of the data quality, and yeah, and it's often faster. We can manually draw masks here by, I think in FSL View, it's in File, Create Mask. This means that now we have a new kind of nifty copy that's empty down there. In File and Create Mask. On FSLIs, it looks slightly different. And for example, if you want to, well, let's not worry about the FSLIs now. So now we have an empty image, and we can draw within that with this kind of little drawing tool in FSL View. And the default would be that you draw with pen size 1 and you draw a value of 1. So let's just draw, for example, the CSF gray matter border like that. everything that's kind of black, and maybe we draw a bit more, how much you like in any slice you choose. I'm now in slice number 6. You can do this in 3D too if you have a lot of time, which we right now don't. So my convention is that CSF and gray matter border is drawn with 1s. Then we can go to values of 2, and now we can draw the gray matter white matter border with 2s. Obviously, if you use like Alessius clustering or CBS tools, you can get this automatically or from the vertices. Also, the algorithm later will expect you to know where gray matter is, so we need to fill it up. In fact, I think I drew it a bit wrong here, so let's remove those and fill it up again with 2s. So I've changed my drawing value to 3, close my borders right over there. There's a bit of delay on the server, maybe because we are all on it now. So now we have a closed volume, so we can use the bucket in FSL view. In FSLIs it's slightly different, or in ITK Snap 2, we just fill it, and then it's all, everything that's gray matter is now filled with 3s. All right, are we all on the same page with respect to that? Did everybody draw a bit?
Super slow.
Super slow?
Yeah.
Yeah. So I'll give you a minute then. Yes. Right, you can. I would, here you're almost perpendicular, so I would go a bit down, maybe draw here. Your windowing is kind of weird from the roof, so maybe you can go there and change it to 8. And this is kind of small too, with control. Bigger there. You can zoom in a bit with the here you have a kind of nice surface. You would fill it down a bit better. Now we want to draw, and I'm not sure why it doesn't allow you to draw. Maybe it's not blue. Yeah, now it allows you. So you have a hand draw here. So you just have it in there. And now you can draw with value of 1, which you want to draw. You draw with 2s. Over there. It's not perfect. Does anybody have problems or questions?
So if I want to do multiple slices, I can also do it.
Sure, obviously, of course, yeah. It's the algorithm is in 3D.
Ah,
Yeah, so you can do like you can there's a flag later that if you want to do it in 2D only, you can. But
I see, I see.
you can, of course, it's 3D. In fact, I would recommend you to do it in 3D unless you're really, really sure that you're perpendicular to the cortex, which is not an easy thing to get. Yeah. I would do it in 3D. But now, for the sake of going through it fast, we do it. We just draw layers in one slice. Okay, are you all ready to continue? All right. Then we need to save that, and we can save that in File, Save As, and I would save it as rim.nifty. Save. So now when we go to our terminal, we should have a file that's called rimnifty.gset. And that's annoying, and even though we kind of set the output file type to nifty. So we need to change it to nifties. We can do that quickly in AFNI. In order to use AFNI, we need to set the path again with this one, and then in AFNI with 3D copy, we copy the rim.nii.gset to rim.nifty. And now we should have a file that's rim.nifty.
So you just unzip it?
You could. It comes along with challenges because of the file type and the way how the nifty header is. Like in the nifty header, you have a slope. I can show you what it does. I need to mount it real quick. I will be there in a second. So where do I have it?
Is there a reason that you use AFNI for the unzipping portion?
Because I know how it works and that it doesn't screw up the headers. Like you can have different slopes for positive and negative values, and FSL might do the same thing. Unzipping it might really depend on the unzipping algorithm, how it does it. And I want to show you why. So now I have, this would be the rim file. Of course it takes a while because we are slow. So here you see that rim.nifty has a range between 0 and 3. The rim nifty has a range from 0.0 to something. And it's saved in this range as 16-bit integers, and then you have in the header you have a scale factor that puts it back that the values that we drew are 1, 2, 3. However, depending on the range you have, especially with 16-bit, it does not always end up with 1, 2, 3, but it ends up with 0.9999999, and then the following algorithms might fail because they are looking for ones and not for 0.9999999s. And that's annoying, and I'm not sure why FSL view it. And with the FSLIs, by the way, you don't have this problem anymore. And I'm not sure why it doesn't, on the server, it doesn't save it as nifty, even though we tell it to. Maybe there's something in the FSL setup here. Yeah. Okay. So now everybody should have a file in their folder that's called rim.nifty, right? Which is the same thing that we drew, it's just a different file format. So now we can start to do a layering, and for that we use LAYNII. In order to be able to use LAYNII, we need to set the path again, which would be this line in the Google Docs. And then we can run ln_grow layers. And if you just run it without arguments, it tells you what it expects. So it expects a rim file with in the syntax of -rim and then the file name. You can give it the number of layers. If you don't do that, it's not too bad. It will just choose 20. And it also will give you, you can have the option of vicinity. So this is, for example, if you have areas of cortical thickness that are very, very big. So if your resolution is so high that you have more than 40 voxels within your gray matter, then this algorithm might not fail. Maybe I explain you how this algorithm works after we applied it. for almost all the applications that I can think of, you don't need to specify the vicinity. It will just 40 will be enough. Here, if you want to do it in 2D or 3D, you can also give it a 3D or 2D flag. So now we give it the rim file, rim.nifty. This starts now. It does some growing from white matter, from CSF, and corrects for some so-called Pythagoras errors, which I can go through in a second what they are. It's not really important. The important thing is that now we should have a new file that's called layers.nifty. So let's look at that in FSL view. We add another file and look at the layers.nifty. And now we should have something that looks like that, which is a voxel map where the intensity of every voxel is an indication of the position of the voxel with respect to cortical depth. Maybe something like this works. Now this looks random. I forgot which one is a good one in FSL view. Hot maybe. Well, you see we have layers. And right, and now I can explain you how this algorithm works. It's kind of very simple trigonometry. This is the wrong link, sorry. So it's basically a crawling algorithm. So we start with the manually drawn CSF border, and then it just grows step by step by step by step to get towards distances. As you can see, this is on a voxel by voxel basis, so one step to the right and one step to the front is always one step. This means that to have a diagonal direction, you have two steps, even though the distance is only square root of 2. Therefore, in the next step, I correct this kind of Pythagoras error by smoothing it along the distance direction, so we have kind of reasonable distances in this topographical space. Next is that I extend the distances to neighboring columns, which can look like that, based on a nearest neighbor algorithm. This nearest neighbor, however, has the problems that, again, due to Pythagoras, it has sometimes amplifications. Like here, all these green voxels have the nearest neighbor of this one, and it looks like the orange one kind of disappears. So this is, again, corrected to have columnar consistencies in the next step of the algorithm, which then looks like that. And this is basically everything that we need. Now we have kind of columns or layers. The algorithm is the same in this voxel grid. Maybe one important thing to note here is that when you can also change the number of layers, not based on voxel steps, but just scaling it later allows you to choose any number of layers you want, for example, as done here. So it's basically just trigonometry. It's only looking at distances with some inherent assumption that kind of every voxel in white matter must have a nearest voxel at CSF. And this can have some implications, and this is not specific to this algorithm, but kind of to any kind of layering algorithm altogether. Namely that we usually assume that the cortical folding the folding radius is much, much, much larger than the cortical thickness. If not, we have trouble. For example, here, this is an example from a cat visual cortex, actually from somebody from CMRR who asked for it once. And in cat visual cortex, you have the problem sometimes that you have folding patterns where the folding has a curvature radius much, much, much smaller than your cortical thickness. And also, you have sometimes problems that when you have weird folding, that the kind of columns have larger thicknesses on the surface compared to the deeper layers. So maybe to be very extreme about it, let's say this is CSF, this is white matter. If you have some kind of geometry like that, things get weird, right? The middle layer might be, what would be the middle layer? It's unclear, right? We can decide to do it like that. We can also decide to do it like that. It doesn't really make sense to say that here this point would have the columns to this kind of little pimple or bump over there. So we have some certain assumptions of the brain geometry. We need to have them to have a decent like working algorithm that's also stable. So if the curvature radius is much smaller than your cortical thickness, then things can get weird. For this algorithm, as for free surfer or any other ones. And maybe you can check out Kendrick Kay's paper on that too, or what Jonathan said yesterday. Okay, this is the overall algorithm. So next we can see what kind of tools we have, what other options we have in this growing algorithm. So for example, we can choose the number of layers. So here, for example, we can choose -n to have, I don't know, 5 layers, something like that. Then it does it again. And again, we have a new file name, layers_nifty, which we can look at. And now we should have only 5 values. And we only have 5. So you can choose how many you want. I think you can choose whatever you like. Of course, the more layers you have, the less partial volume you have across cortical depth. So I would always advise to use more layers than you have resolution for. Some people feel offended because they think that using more layers than you have resolution for would implicitly suggest that you have the resolution for like 100 layers, even though you don't have that. Yeah, I don't mind this kind of criticism. Also, some people say that if you choose 6 layers, it inherently implies that you're referring to cytoarchitectonically defined layers, which is also stupid because it's just one definition of cytoarchitectonical defined layers. In fact, if you look at this table that Farouk found in an old textbook, you can see that there, like, for some weird historic reason, people choose the Brodmann definition of the layers, right? But everybody, like in the early days, chose their own definition, right? So you shouldn't use 5 layers either, because then they would say, oh, you refer to Bolton layers, or you shouldn't use 9, then you refer to Cajal layers. Choose whatever you like, I would say.
Where did you find this?
Yeah, I was going to ask.
Farouk?
It's an amazing table.
Yeah.
I've done a PhD in this stuff, but I never found this. It's
Yeah.
amazing.
Right, I think there are, maybe I have a good reference. I think it's this one. Like this is Cajal. Like here he has 5. This is the table that Farouk found, and this is from Anatomie, Entwicklung, Missbildungen, Vererbung. From
Was discovered by Farouk.
Yeah.
Very good acknowledgement.
Yeah, sure, yeah.
That find is really quite impressive.
Right.
Which post was this?
And this is the terminology post. If we call it layers or submillimeter or mesoscopic or cortical depth or whatever, true laminar or mesoscopic, I said that already. I have a similar opinion on that. Choose the term that you really like. Depth resolved. The title of our workshop is depth resolved. It's not even included here. Should include it. So, with respect to the number of layers, maybe I need to show you maybe an explanation why I would advise you to use more layers than you have resolution for. Like here, for example, if you have like only 3 layers, the layers are thicker. This means that an individual layer, maybe I have this clearer here, when the layers are thicker here, this layer that is outlined in blue pooled signal from this stripe of neural activity and this stripe of neural activity. So the thicker your layer, the less resolution you have. Basically, you reduce partial volume. Of course, you can overdo it in the sense that when you have too high resolution, like 100 layers, then the layer might not be connected anymore. And then you run into this problem that Jonathan talked yesterday, that you are rank deficient. So you need to choose your number of layers, kind of keeping in the back of your brain how big your ROI is. Obviously, the ultimate true way of doing choosing the number of layers is that every voxel has a certain cortical depth, every voxel centroid, and then every voxel is its own layer. And you just, if you miss some cortical depth because you don't have a voxel, then you just miss it. And then you need to adjust your statistical testing tools at the end. Like similarly, when you do a time course analysis in GLM, sometimes you censor data points that are where you have motion, and then you just have a missing data point, and you need to acknowledge that in your statistical analysis. But it doesn't mean that that you need to interpolate it or anything. Just use the data points that you have without any bin size at all. So, but if you have need to choose bin sizes, choose the bins as small as possible. Maybe the animation up there is explaining this more intuitively here, where I use a toy example of like 2 layers, 3 layers, 4 layers. At some point you see this Nyquist sampling of the 2 layers in the motor cortex. If you overdo it, like 100 layers, then you see that you get weird noise patterns because we just don't have 100 voxels within our field of view. Okay. Here, so I think here we might be good in this example with anything from 10 layers to 20 or so. But you can play around with that, and we did that just now. Another thing that we might want to play around with is, for example, this option that is called thin. So when you have only a very small part of the brain, like in this example, Jonathan yesterday showed that you're rank deficient, and you can account for that bias that superficial and deeper layers have more voxels by using the thin option, which does some redistribution of that. So for example, if we do minus thin now and compare that, you will see that the layers are slightly shifted. Not in this one, sorry. I want to view it in this one on the server. Sorry. Add. Now we have a new layers, which is kind of like amplifying the superficial and deeper ones. So this is both 5 layers, but they're now differently distributed across the cortical depth. And this is I would not really use that unless you use like 2 or 3 layers. Then you need to do this redistribution. And this is, I think, done for InSub originally, who does some orientation decoding across layers with Sonji Kim. All right. Do you have any questions about that? Yeah. Right.
So in your algorithm, it's like nearest neighbors you are taking,
Mm-hmm.
but instead of that, we can also play around with other kind of algorithms,
Like equivolume or equidistant one. Like this is most closely related to an equidistant one, as I.
But it's for example, the clustering problem also, right? We can also make it without defining number of clusters. We can also ask this to cluster and then bring the data back.
Should you, like you can use any algorithm you choose.
Is there any reason to choose this one because it's more easy?
I tested a few, especially the equivolume, equidistant, some repetitive smoothing, and then you have some leakage layers. I like this because it's not too far away from the truth, and because it's super robust against noise. So, for example, you saw that our original, like the RIM file that's used to calculate these layers, we have weird bumps. It's not super smooth. And as I might have alluded to with a comment to Jonathan yesterday, the equivolume approach, it's really sensitive to these kind of bumps. It over amplifies the curvature. So if you have noise, it over amplifies the noise. And that can be really challenging. You don't need to worry about that with FreeSurfer because it kind of smoothes the cortical ribbon. However, as soon as you smooth and have smooth folding patterns, then you always have some biases for sulci versus gyri. So I chose that algorithm because it works and because it doesn't have this noise problem. Ultimately, I think if you have very, very high resolution, you would want to use the equivolume approach. But you can describe it as a clustering algorithm too, or whatever you like. Yeah.
And the layerification or layer definition, you do it after processing the data, like with the T map, or because pre-processing thing or in the post-processing step we
Right. I never really understood the difference between pre and post, or like it depends where you. I usually do it in EPI, so I need to have some mean EPI image like the one we are looking at right now. So that's all you would need to do the layering.
Then in the mean EPA you have, for example, it's already motion corrected. And
Yes, yeah.
Noise reduced.
Right, averaging is some sort of noise reduction, yeah, right. You need to have some EPI, and you need to have use the same space that you have also for the functional data. Here, the mean is obviously the same data that are used for the functional data, so it's inherently in the same space. So I guess you would call that after the pre-processing then, I guess, yeah.
So when you do the GLM, so you do it before layering.
I do it kind of parallel, right? Like you have your time series, you motion correct it, then on one branch of your pipeline you do a mean where you can do the layering. On the other branch of the pipeline you can do your GLM or whatever kind of functional analysis you want to have. And they're all in the same space because they originate from the same data. So you can do it before or after, whatever you like.
So you have to upsample your image first.
Well, in this case, this is the native resolution. If you want to have a lot of layers, you need to upsample it, and we can do that in the next step. Yeah. So, and for that one, you can do it before or after GLM, but if you do it before your GLM, then your data size becomes very, very big. So in this case, you would do it like after your GLM.
So I'm wondering from Kamil's presentation today morning,
Mm-hmm.
and he showed maybe go near the borders, it's kind of going up, right? And this need to be corrected in somehow with the noise reduction steps. Like I usually with the 3 Tesla data, we use NCR, noise covariance reduction,
Okay.
which we put the motion parameters and first order linear trends and also some physiology, everything in a single step we regress out.
Mm-hmm.
So I thought we should also regress this kind of stuff at that step so that our data will be more.
Right.
That's what I was
Right.
talking about. For that kind
Right.
of definition, I need the layering.
Right.
The meaning, right?
I think it's rather independent, right? The layering, you can extract the
No,
layer.
It's a question like whether I want to do the stuff which Kamil said.
Mhm.
If I'm not going to do it, then it's perfect. But if I want to do that, then I need the layering. Which I want. I
Right.
also don't want to regress everything in separate step. I want to do everything in one step because that's
Right.
what FMRI people do nowadays.
Right.
So
Right.
that's why I will try on
Right.
and see whether
Right.
it makes difference.
Sure, yeah, do it, yeah. Sounds interesting. Yeah.
Do you have any opinions on the estimation of the borders of, I mean, here you have pretty nice resolution, because I think is this isotropic resolution?
Almost. The slices are a bit thinner than in plane. It's 0.54, 0.54, 0.53. So it's almost isotropic, yeah. Which,
So,
yeah.
In general, let's say we were not collecting half-millimeter scans where you can pretty well delineate
Mhm.
the gray matter borders, but we were using something like the multi-inversion API
Mhm.
at 0.8 or 0.75. Do you have opinions on the accuracy of the gray matter border when you're using the difference between an anatomical
Right.
image that's collected at a much higher resolution versus something like a distortion corrected
Right.
or distorted T1
Right.
image, etc.?
I think it's an important point, and I'm not sure if I have if like there are multiple dimensions to that question. Maybe one is that the gray matter white matter borderline here is kind of fixed to your voxel grid, which can be a problem if your resolution is too coarse. Then you need to upsample, and we can do that in the next step, which I usually do. It's a kind of additional abstraction level. On the other hand, and maybe your question refers to what I asked Jonathan yesterday when he has like 0.75 millimeter anatomical, and then the accuracy of your gray matter white matter border is in a range of 250 micron, which is kind of hard to comprehend for me. I think it makes sense, but yeah, it's hard, especially also considering that different parts of the brain have different gray matter values. So your partial voluming model is always kind of biased.
Yeah.
Right? Or for example, like also, you would choose your gray matter CSF border at a voxel that is half filled with CSF, half filled with gray matter, right? That would be the ideal point, or the most sensible definition. Now, when you have a kissing gyrus, there might not be any voxel where you have half filled CSF, half filled gray matter. So there, you need to choose a different definition, and then you have kind of a folding-based bias in your gray matter CSF borderline, which is also a problem. I don't know how to deal with that. I usually try to be very conservative in the sense that when I draw my rim mask, maybe I can remove the inner so you see it better. I try to kind of don't really draw it at the borderline between gray matter and white matter, but more draw it at the white matter. So for example, like here, if you see it, I kind of make it the upper layer of white matter. So I always try to be more inclusive and then cut it later in the profiles.
Makes sense. And do you feel like, so obviously in some ways you can gain information by upsampling your data, but of course, if you kind of make the assumption that the only information that you really want to get at is gray matter information, then theoretically you would be gaining more within gray matter than at the border. Do you feel like that affects things? Because then you're kind of splitting up voxels that are in this border area where their intensities are changing. Does that make sense?
I'm not sure if I understand it.
So in the middle of gray matter,
Right?
we would assume that the whole voxel in the original resolution had information about
Right.
functional activity.
Right.
But at the edge, you're probably losing
Right.
some of that.
Right.
So some of that statistical power will go into outside of your ROI, and some
Right.
of it will go into your
Right.
ROI. And I'm curious if you have any thoughts on whether that's an effect. The reason I ask kind of is because it sounds like part of Cheryl's goal is to kind of get,
Right.
okay, what are the rules
Right.
of what's acceptable and what's not? And one of those things might be upsampling data. Obviously, some people are very against it, and some people think that it helps for things like clearing.
I don't see any reason why not upsampling it. Of course, it depends on your kind of, like nearest neighbor upsampling is basically keeping the same and just having more smooth gray matter white matter borders. I think I don't have an answer. Yeah. I think upsampling never really hurts. Of course, it depends on your statistical analysis at the end. For example, Camille earlier said that you can do divisions, right, between different contrasts, like do contrast response A divided by contrast response B. And there, your problems are, your issue is a huge problem, right? Because if you have a voxel that's only half filled with information, then you're dividing by a small number, and your ratio might explode. So it depends. I am very skeptical. I shouldn't record this. I will not say anything about it. Yeah. So yeah. Let's upsample it and look at it. Okay. There is a subfolder that's called scaled, and let me just look into that to see what's in there. There's nothing in there. So let's copy our activation and T1 files into that folder. And I think I prepared that here. So let's go into the scaled folder and copy the mean vaso, the bold activation, and the vaso activation into that folder. So the content of your folder should now look like this. And there's already a script in there that's called upsample. So let's look at that. This is an AFNI command that basically divides your resolution by a factor of 3. You can choose your interpolation function. Here I use cubic. You can use nearest neighbor. There people really have different opinions. I see the way how we acquire data as like they call it voxels, but actually it's I see it as having a rectangular grid where we have a sparse sampling and we sample points like voxel centroid values. Yesterday, Jonathan talked about Peter Koopman's way of analyzing things, where if you plot a line over here, you have kind of a step function, which would assume that the voxel is homogeneously filled. So some people think this is the most conservative way of thinking it, that a voxel is homogeneously filled with a value. I don't think so. The way how k-space works is that we have a centroid, and that's kind of an overall weighted average of the entire signal in there. So the only information we have is the voxel centroid location and the value of that. So I don't see that we should like use nearest neighbor interpolation and assume that the voxel is homogeneously filled. It's a weird assumption.
Would you, I mean, but there is blurring, obviously, so would it be preferable to you that they were not modeled as blocks, but instead as Gaussians, or?
I think it would be more accurate. I don't know if Gaussian is the best, or some other interpolation function, or like Lorentzian because it's k-space. I don't know, but it's a strong assumption to assume that it's homogeneously filled. I know that Martin Havlicek likes nearest neighbor. I think Camille too. Overall, we are at the borderline of what you can see within the voxel grid. So if your result depends on the interpolation function, don't trust it anyway, I would say. But you can like push it a bit or reduce this one effect by including another one. I like linear or higher than linear interpolation functions. But people say that if you have that, then you might introduce wiggle or Gibbs ringing artifacts and put stuff into your data that might not have been there originally. So each interpolation function has its like advantages and disadvantages. If your result depends on it, don't trust it anyway. Yeah.
Can I ask a question about that?
Yeah.
What is better, bicycle or plane?
Wait.
Do you see the what I'm after? What is better, nearest neighbor or spline interpolation? It depends on what you want, right?
Right.
So that's the reason I'm throwing this one in again.
And I think I had a post about that.
Basically, I just want to say, I absolutely agree with you that if this is going to make the difference,
I think linear is blurring things. Spline looks crisper, but it has maybe some noise amplification, or maybe it better contains the noise. Here are different splines that almost don't make any difference. Nearest neighbor, here look at nearest neighbor. You have, like, obviously you have these weird effects. Maybe you can see it, I'm not sure. Like here, you have a step between one slice and the other, and so it puts some weird edge into this sulcus that was not there originally. This makes me afraid of using nearest neighbor.
Sure.
And you asked about.
So yesterday you showed a very nice spider graph, different sequences, different strengths and then weaknesses. You could make the same type of spider graph for interpolation methods.
Absolutely,
right?
yeah.
So.
Right. Okay, so let's scale it. We have this little AFNI script, which basically the first step is to save or to figure out what the actual resolution is right now, divide it by 3, and then using a 3D resample command from AFNI to resample it with a certain interpolation function. You can comment it out here and use the nearest neighbor instead if you want. And so let's do that together. We can execute that with up a sample, and then let's upsample the mean. This takes a second. I'm not sure why it takes so long. Maybe because we're all on the server. So now our resolution is 0.18, 0.18, 0.176666. So it's divided by a factor of 3. We do this with all. Let's do this also with the VESO. We actually have 20 minutes left only, so let's be quick here. And the same thing with the bold, because we want to look at some layer profiles at the end. I promised you that we get towards something that looks like this one. Okay, now I hope you're all there, so we can again look at the data, FSL view. Hopefully our path is FSL view. Our path is still active. Then we have 3 files now: the scaled underscore bold, scaled underscore mean, VASO, scaled underscore VASO. So now let's just only open the mean to quickly redraw the layers that we can work in this space now. Again, I'm hitting Control 1 here to look at it slightly bigger. And after upscaling, it always looks nicer. So here, for example, let's go a bit down again. There's some huge delay. You might even see the stria slightly better if you wanted to see. Okay, it stopped. So now again, I'm drawing the rim. Create mask. We have a mask. So again, now I'm drawing with ones. Let's again focus on this one. Then with here you can obviously draw the gray matter, white matter borderline on a much finer scale. And this is actually, usually I work in this upsampled space. Not really because it's easier to draw, but because you not always have 0.5 millimeter resolution data. Or it comes at a price to have 0.5 millimeter resolution data.
Unless you upsample it.
Right, unless you upsample it. So again, I'm closing it with 3s, and now I'm filling it with 3s. And I'm quickly saving it again as rim file, rim.nifty. And maybe now at BBLS, it's again saved as rim.nifty, so I'll quickly copy that command again. Sean, you want to say something?
I just wonder, the interior boundary, the one that you drew there, seemed as if it was just 2 segments. It didn't matter that it was not a continuous. It didn't look like you followed the loop all the way into the sulcus and out again. That doesn't matter?
It should, yeah. It depends on the question, I guess. Now I want to show you how bold and VASO is different. So whatever kind of bias we have, it's similar in bold and in VASO, or in task condition A and B. Okay. Of course, later you want to have proper boundaries. Right. You are saying that.
No, yeah, no, it just didn't seem as if. Anyways, it doesn't
so matter. Here the accuracy was kind of bad. You're saying.
No, it was the.
Here.
On the interior, sorry, on the.
Somewhere here.
It's okay.
Okay. Yeah. And there was also a delay, right? You drew, and then it kind of interpolates into mouse chunks. Okay. It should. Usually we should focus better on a good. Now I quickly need to fix the nifty or nifty gset again. Where was the command? This one. If you want me to slow down because you don't follow, let me know. So now we have the nifty again. So again, I can calculate the layers with ln underscore grow layers minus rim dot and the file name is rim.nifty. This takes a bit longer now, so this is starting to grow from white matter now. Hopefully it starts to grow from CSF soon. So now the data files, even though it's a single TR image, is in the range of maybe 250 megabytes already for 16-bit integer. No, oh wow, this is a 64-bit, that's why it's huge. Not sure why it did that. Hopefully it comes in a second. Is it faster for you? You're not doing it. No. Okay, so now let's look at it, how it looks. Maybe it's nice and smooth. Maybe there's something wrong. Let's see. Loading it. Okay, there it is. I forgot which one was a good one. Render one, maybe. Kind of. And you see its layers. And again, I didn't choose any number of layers, so the default is 20. So now we want to extract the signal from every layer from a given activity map. And for that, I have prepared a script that is now not in, that is here, afni_layinii. So let's look at that. This is using an afni command that's called 3D ROI stats. And this basically estimates the mean within the mask, here the mean, the standard deviation, and the number of voxels, and writes that in a text file. So let's quickly do that. Afni. And now we want a scaled, for example, the bold one. So now we extract the signals from each layer and we get these kind of profiles. In the way this is set up, it gives us 3 lines. The first line is the number of voxels within each layer. The second line is the standard deviation in each layer. And the third line is the mean within each layer. And now we did this with bold. So you see that we have kind of a bias that we have more deep layers, more voxels in deep layers than in the superficial layers. And this is simply due to the curvature, because we have a sulcus and not a gyrus. So here for this segment, we just have a few more voxels in the deeper layers compared to the superficial ones. The standard deviation increases towards the superficial layers as expected and as shown from Jonathan. This might be mostly due to physiological noise, because somewhere here we have this elbow shape. So here we don't have any leakage from peel veins anymore, and it's more flat. We see, if you want to see it, that we have this huge peak at the superficial layers from the veins. Maybe there's a shoulder there, what Koopmans also showed 2010 already. Let's look at this now in bold and vaso for comparison. I kill this background, and I do the same thing for, not for bold, but for vaso. Then we can compare it. Okay, this is the vaso. We have obviously the same RI, so the number of voxels across layers are the same. Here we have a slightly different variance across each layers. There's not this huge bias towards the superficial layers, because we don't have this huge physiological noise from the large veins, because we're not sensitive to the large veins to begin with. However, we still are sensitive to CSF fluctuations, so we still have a peak over there. Overall, if you compare the black line here, the mean signal, and the mean signal here, it looks rather similar, with the only difference that the superficial layers are kind of suppressed in blood volume fMRI. So here we are not sensitive to the large veins, or at least I believe that we are not sensitive to the large veins. So, and some people use that to claim that the vaso is more sensitive and more specific, locally specific to the layers, which is kind of the reason why I use the vaso to begin with. Maybe let's look at also at the T1. Let's see if we get something out of that. A scaled mean vaso. So this would be the mean vaso, where I'm not sure. If we would see the stria of Gennari, then we should have a dip here. It's not a clear dip in the mean. In the standard deviation, we see that the signal is more consistent within the stria of Gennari. Not sure what that means. It's definitely not a linear curve. If you would look at the very difference to a linear distribution, you might be able to see a dip or a plateau, which you could interpret as a tree of Gennari. And this might also be better visible if you use a smaller field of view or draw the layers more accurately, as Sean suggested I should do. Right. So now we have these kind of profiles. And if you want to look at, and what you see here is just an AFNI viewing of a text file, cut, that is called layers.dat. So where you have three, like in an ASCII file, you have three columns. The number of voxels is here. This would be the standard deviation, and this would be the mean. Right. Do you have any questions about that? Do you get similar profiles with your drawn masks? Did anybody draw the masks?
So the layer dot data, so that was generated by your phone?
This text file is generated with this script, and
You don't have to input your layer file?
let's look at that script. This script is basically this command. It's an AFNI command that looks for the layer nifty file as a mask. So it basically estimates the mean value of every value in the mask. We have now 20 different integer values in that mask, and it averages the signal within each mask. We want it in a 1D format. We want it to be quiet. We want to get the mean, not the sigma or anything, and we want to dump it into a file that's called layer_dat, which would be this one. This one, however, is switched, like it's a transposed version, so you don't have columns as an ASCII file, but you have lines as an ASCII file. So this is what I kind of do back there, that I change columns with lines. So that's why I have two layer.dat files, one layer_t.dat and one layer.dat. So this AFNI command, or the script in the AFNI command, expects that you have a file that's called layer.nifty. Yeah. Right. If you don't have that, it will complain. Are there any other questions?
So, if I want to do this for a couple of slides,
Right.
is that possible?
Absolutely. Like the layering algorithm is a 3D algorithm. It's like it's a growing a distance metric, and that's 3D inherently.
Right.
You
So
can-
the 2D example was just for convenience, right?
Right, for now, yeah.
Yeah.
Right. Especially in the visual cortex, you need to do it in 3D, right? Yeah.
Yeah, definitely.
Yeah.
Anywhere when you've got.
Right. Or in fact, 2D might even be wrong, right? If we have a sulcus like that,
Yeah.
and then you cut it kind of here, then who knows what, like this. It's a cortex is 3D, so we need to do it in 3D. Yeah. Right. Or like these weird things. It could be that we have white matter in the third dimension, and it all makes sense. Yeah.
Yeah.
Yeah. Right.
Is your upsampling always done in image space, or do you alternatively upsample case-based data?
I did both. I don't see a huge difference. Valentin Kemper gets credit here. At the scanner, you can upsample the images in K-space. I didn't find it so convenient, mostly because that time our scanner hard drive was limited and your data becomes so huge. And so the export to your local machine, the motion correction, everything is slowed down so much. So I found it easier from a logistics perspective to upsample it later. Yeah. But of course, if you upsample before, then you don't have all these resolution losses that Jonathan talked about, these resampling issues. Yeah. Of course, upsampling in K-space kind of also answers the question of which interpolation functions to use, right? Then you cannot really lose anything if you upsample in K-space, right? Because that's all the data you acquired. You're not putting any features there that You don't agree?
No.
No. Okay.
We ended a little early because I was backseat driving from inside the scanner, but we
Okay.
wrapped up there. But we did not even get around to running the T1 API on my head.
Okay.
So, but you know, if you guys
Yeah.
wrap up in the next 10 minutes.
We
so
are
it's-
actually done, I think.
Yeah. So
Right.
I'm gonna go get some coffee. If there's
Okay.
coffee today.
Do you have any more questions?
Just a quick one.
Yeah.
Well, no, it's not a quick one. It's a discussion question, I suppose. Do you have an idea of the nominal resolution or whatever we're going to call it? How many layers? Just in the month we just drew.
Mhm.
What is your opinion? About the number of layers that can meaningfully disentangle?
It's a question that I should ask you. I think you thought about these partial volumings much more. I think for the analysis perspective, use as many as you can. That like upsample it. Like the more layers you have, the less partial voluming you have, right? Like in any histogram analysis, you want to have smaller bins, but if your bins are too small, then your noise might be too big. So you need to find a compromise there. And depending on the noise level you have, the RI size you have, there's a sweet spot. For like quantifying which kind of independent like data points you have across layers, it's a different story. Like especially for statistical analysis, when you want to like see if the upper layers behave differently than the deeper layers, you need to quantify how much partial voluming they have, and so on.
Right. So I suppose that leads to quite a different question. What kind of questions do you think you can answer with this type of analysis? Because let me rephrase that. You're looking for some layer-specific effect, right? But when is that layer-specific effect reliable? So the Goldman's dip, for example, if you just see that visually, would that be convincing, or would you want some statistical measure on top of that?
I think we always need to convince ourselves, not only from the resolution perspective, but also from the vascular density perspective. We need to make sure that any result that we see is not just a scaled version of the vascular density. So I think whatever you do, you need to compare it with something. Like, for example, two different task conditions or so. And as soon as those different task conditions are not scaled versions of each other, I think then we can answer a question. If you only have one task condition, it's hard. So,
okay, sure, I agree. But then, now, how does that relate to the number of layers? Because when you've got 30 layers, it's a lot easier to visually see it than if you only compute 5, right?
Right. Then I would go for 30. Right? If they if all the 30 layers have a lot of shared sources of signal, then you wouldn't see the dip, right? Then it would be just a smooth line. But if you see something with 30, then it makes sense. Like, for example, like in this animation that I had, like with 4 layers or with 2 layers, you just don't see it. But with 20 layers, you see that there are 2 things. So then I would go for as many as you can.
Right, okay, but then that leads to the question, if now in a paper over subjects or regions of interest, I want to indeed claim that there is the dip, what kind of metric should I report to indeed make that claim? I can see it.
Right.
But seeing that, is that enough? Especially if I want to average over multiple subjects.
Right. I think like the ultimate point is what Ravi Menon originally did, right? That say that every voxel is its own layer. Don't bin it at all. Just look at the signal versus the respective cortical depth. And then you can use any kind of statistical analysis you want that you usually have in these kind of point clouds.
Hey,
I don't know how people
There
do
are not
this.
that many.
Right.
Well,
right.
like, now we're getting into the what's better, a bike or a plane again question again, because.
Like for example,
you
for
have a
this kind
point
of
cloud.
analysis, there are a lot of statistical tests to say if it's unimodal or bimodal.
But that's exactly
Right.
the point. There are so many
Right.
that, well, then you're only going to choose the metric
Right.
that shows the thing you want
Right.
to see.
Well,
so that's what post hoc. So that's why I'm just wondering if we can.
I mean, like, look, I mean, all these models, they are consistent. You start with 3 axioms and you build the math and statistics. They're all consistent if you use them the way they're supposed to be used. So it's not like you can do post hoc whatever you want, right?
Right, but in what way are point cloud statistics supposed to be used? That's the difficulty. So now with that question, you're just moving the goalpost, right?
I'm just gonna come in and sit over there.
And I don't have a clear answer. I'm just saying that it's a hard question,
Right.
and that's something I would be very interested to hear your opinions about. What kind of statistics can we do on this type of level of data?
Right.
I think the long-term goal is to somehow relate the function to something else. So if you see a shape like that, you also see a shape like that in anatomy. Or if you went to another data set, if you had, I don't know, spine density or something like this. We don't have that, so it's relatively exploratory. So in that sense, it makes sense to just report it as an exploratory analysis in a lot of ways.
Yeah.
But beyond that, we want to lay the groundwork so that we can make these relationships.
Exactly.
Somewhere.
Yeah, I agree. So if you see a point cloud like this, and the purple line you drew, that's already confidence interval. But what you could do, for example, is say, right, well, that looks like an x to the power 4-ish function. So let's pick those 5 parameters and test those 5 parameters. That's a way.
I think we're done.
It's not the only way.
Sure.
All right, I'm gonna call a